In section 2B, we're going to be looking at the metric system. The metric system is primarily a way of working with units that is done in other countries. In America, we have what's called the US system, which is a little bit goofy. That would include things like quarts and gallons and inches and feet, and things that like the counts are really unusual, like 12 inches makes a foot and 4 quarts makes a gallon. 3 teaspoons makes a tablespoon. They're all just kind of weird numbers. But the metric system, everything's based on tens. Basically, any unit that you take, if you were to take 10 of those little units, like say you have a little unit, you take 10 of those, it becomes the next size unit. And if you take 10 of those, then it becomes the next one from there, versus like our weird system of 4 makes a new one, or 3 makes a new one, or 12 inches makes a foot, like where all that comes from. All right, the metric system is mostly used with 3 general types of things that we want to take measurements of. The first would be distance or length, and we have these things that are called base units for them. The base unit for length is going to be meters. The next thing that we look at is volume. The base unit for volume is going to be liters, and then we also have what is called mass. Mass, you can sort of think of it as weight. There's slight differences in what they are, but for the most part, you can just consider mass as the idea of weight, and the base unit for that one is going to be grams. There's other stuff out there that we measure like time, but these are the big 3 that we usually study in a class, and once you get the hang of these, then the other stuff that's out there, like other things that you can measure like time, you can easily adjust to looking at those things. All right, within this system, we do a lot of abbreviating with things. Meters are going to be abbreviated as M. Liters are going to be abbreviated as L. They have a capital L here. It doesn't actually have to be a capital letter. It's just, I think we're using a capital L so that it doesn't look like it might be a capital I. Grams are going to be with a G. All right, a couple of quick questions here. If we're going to be measuring the height of a bottle, which of these base units is going to be the best to choose? And that would be meters, because it is a type of measurement in length. Now, meters are about the size of a yardstick, so approximately 3 feet. So you might not want to measure the height of a bottle with some kind of unit that's really large like that. You want something a little bit smaller. So we'd probably use what are called centimeters, and we'll talk about the different versions of meters that you can use, but you know, there's smaller increments that are available. The weight of a bottle of soda, we would do that one in grams. That's kind of tricky to how like we deal with weight, because our, like in the US system, it gets a little bit mixed up when we talk about volume and weight, because we can use ounces as a volume and also as like a weight type unit. So this one's a little bit better here, that the weight is going to be in grams and then the volume is going to be in liters. Let's see, and all right, number 2, that's going to be a little bit odd because we haven't talked about all these different versions of things. I did mention that we might do like centimeters. You can do, if it's really big distances that we talk about, not something that's just like the length of a bottle, you do kilometers and so on. And we have a whole bunch of like variations of these, what we call base units. All right, here's an example, deciliters. Deciliters are a tenth of a liter. Okay, so if you want to talk about something that's a tenth of a liter, you can call it a deciliter, and it's abbreviated as DL. And then you would just read that as deciliters. We also have what is called deca, so where a deciliter is a tenth of something, a deca is going to be 10 of those things. So these are bigger sized items. Decagram is going to be abbreviated as DAG. It does have the letter A in there because both of these things, where they both start with D's on those. All right, question 3 is going to first start to show us, like, because I've talked about this factor of a 10, like a tenth or 10 of these things, but this is something that we can actually draw and show you a real size picture. That gives you the comparison of the tens here. All right, so we have a little caterpillar that, you know what, I just kind of noticed I didn't quite read, or I didn't notice something in the picture that that I was thinking earlier. Oh, I wrote it up here. All right, it says that you're trying to find the length from the tail to the eyeball. I didn't actually go all the way to the eyeball. I just went to the front of the head. I wasn't noticing that the antennas here might actually be the eyeball. So they're trying to measure that out to 3 centimeters. I'm going to keep to the answers that I have here because I like the idea of using the decimal. So I'm going to measure off to just the, I guess, his nose. I don't actually know if he has a nose, but we'll say he does. All right, so that ended up being about 1 mark short of right here. So it's at that one, okay? All right, so using our increments, the centimeters and the millimeters I can actually get like easier because every single one of these lines, no matter the height of them and stuff, each of those is like counting up. So if I count all the way to that one, it's going to give me a total of 29 millimeters. Okay, and then when I'm looking at centimeters, it's going to fall just short of that 3, right? So it's between 2 and 3, and it's going to be 9 of 10 little marks that's in between there, so I would call that 2.9. Okay, so again, I think that they wanted here, and I'm just noticing now that it would actually be 3 and 30, but I kind of like looking at this with the decimal, so I'm going to let it be. Okay, so 29 millimeters and 2.9 centimeters for that. Let's see here. When you measure the worm, did you have more centimeters or millimeters? You're going to have more, right? 29 is greater than 2.9, which is a larger measure, unit of measure, and that'd be centimeters. So centimeters are a larger thing. They're bigger than what a millimeter is. They're about the width of a fingernail, where millimeters kind of like the thickness of a fingernail. All right, so let's see. And then see, what operation can you perform on the number of centimeters, that's the 2.9, to get the number of millimeters? Well, to get from here to there, we're going to multiply by 10. All right, now that we have a single example of how 10 little units is going to make the next size unit, what we want to be able to do is express the changing of that multiplication by using powers of 10. That's going to be all these 10s with the exponents here. 10 millimeters is going to make a centimeter, okay? 100 centimeters is going to make a meter. We haven't looked at that one yet, but centi means 100. So 100 centimeters is going to make a meter. Now 100 is also just times 10 times 10, doing that, which is like a 10 squared. Okay, and then millimeters actually takes 1,000 of those to make a meter. So I'm referring to our base unit here, right? 100 centimeters is getting us to a meter, and then 1,000 millimeters is going to get us to that same meter, and 1,000 is the same idea as times 10 times 10 times 10, doing that 3 times. Okay, all right, now we're going to try and separate a little bit of talking about the units for a moment and just discuss some other general math stuff here, which is how to deal with exponents through multiplying and dividing. All right, so here, what I'm looking at is multiplying 10 to the second power by 10 to the third power. Okay, now, what 10 to the second power represents, if you don't want to look at it as is an exponent, right, is 10 times 10, which is 100. That's all that number is. And just show you here real quick. If we were to square 10, you're going to get 100. Okay, and then if I took 10 and I cubed it, that's going to be 1,000. So really what you're being asked in this question is to multiply the 10 squared by, you're being asked to multiply 100 by 1,000. Okay, so let's see what that does. We take 100, we multiply it by 1,000, and we get that, right? So hopefully you remember a little bit with multiplication and numbers involving zeros that you can just multiply the numbers that are at the beginning of them. So 1 times 1 is 1. And you can also just count up all the zeros that you have. So I had 2 and I had 3, which is going to give me a total of 5. 1, 2, 3, 4, 5. Get a total of 5. So then this number I can actually turn into 10 to a power as 10 to the 5th power, right? Now, you don't really need to go through this whole process every time you're going to do the problem. What we want you to see here and to remember, it has been studied at some point in your time with math classes, that if you're going to multiply these together, you don't need to expand them out, see them as 100 and 1,000 and do all that. You can actually just take their exponents and add them together. 2 plus 3 is going to give you 5. See, that one gave you 2 zeros. This one gave you 3 zeros, so overall you're going to get 5 zeros. Oh, and by the way, all the problems that we're doing here are with what we call a base of a 10, not to be confused with the other bases, meters, liters, grams. But speaking algebraically, the big numbers are called the bases and the little numbers called the exponents. Okay, and if you're using the same base, then these rules can apply. So that's good that they're all going to be 10s here. But it's also really helpful that we're doing 10s because you can think of it as counting zeros that go with it. Okay, so when you multiply, let's add the exponents, even if you have negatives involved here. All right, check out this one. You've got 10 to the negative 6. Now, you might not be able to see or imagine what that one looks like at the moment here. We'll definitely talk about it later with scientific notation. Not scientific notation in these notes, but we'll address that separately later anyway. But we can still apply our rule here. You can take the negative 6 and add the positive 3. Or think of it as 3 minus 6, which gives you negative 3. So this is going to be 10 to the negative 3. Okay, then next, still multiplying here, you can have negative 2 and negative 1. So if you add negative 2 and negative 1 together, you're going to get negative 3. A little negative looks like a dot, so I'm going to extend that out just a little bit. Okay, and then you have division, which we're going to use definitely when we get to the scientific notation type problems. But when you divide them, what you do is subtract. So if you're multiplying, you're going to add exponents. If you're dividing, you're going to be subtracting them. We're going to do the 5 minus 3. So you subtract down. That's going to give you a 2. All right, and then just to show you that one real quick here, if we took 10 to the 5th power, that's just a total of 5 zeros that we have on there. Okay, make sure they're all there. And then I'm dividing it by 1,000. That's 3 zeros. And what you're going to see is our 5 zeros minus 3 zeros is going to get down to 2 zeros. So we're going to see 100 is our answer, which is 10 to the 2nd power. Okay, so subtraction works as well. This is your reciprocal, the one that we were looking at there. So you're still going to subtract down. So we did 3 minus 5, which is going to give you a negative 2. Okay, and then here, maybe the trickiest of all of these, we've got a 2, and then we're going to minus a negative 1. Okay, so this is 2 minus negative 1. If you subtract a negative number, it works as if you were adding them together, which is going to be the same thing as 2 plus 1, which will give you 3. So there's a little bit of tricky algebra stuff mixed in, but I think these cover pretty much all the cases you'll see. Next, what we're going to do is take a look at this table that's been given to us. The purpose of this table is to give you an idea of what all the different prefixes represent. Okay, so we've got our base units. For mass is going to be grams, for volume is going to be liters, for distance is going to be meters, and then these are all the different prefixes that you can put in front of them, and it changes the size of what they are. Like, so there's that centi that I was talking about, so you could do like centimeters, okay? I'm going to tell you right now that my personal thought on the table, it's packaged nicely. You've got them all there in a very small space, but I don't think it's really organized in a way that you might be used to of seeing it in a science class. So if you want, maybe do a little bit more research on this stuff, Google metric system and see if you can see another like table that's written out. The one that I like is, it's a horizontal one, like everything's written horizontal, and that's probably, because there's so many things on here, that's probably the reason they didn't use that one for the activity, but I think it does show you a lot of stuff, so maybe take a little look at something like that. Okay, but what we have the list of all these prefixes. We have a lot, and usually in a science class you only see, so back in the day when you studied this originally, you would have only seen 3 for each of these columns. All right, deca, hecto, and kilo are all the big things. You use these to measure larger stuff. Deci, centi, and milli are going to be used to measure very small things. But then you've got some that extend beyond them. So if you need to measure something that's bigger than like a kilometer type thing, then, which I've never actually seen that done, but these you might recognize here from like computer data, like megabytes, gigabytes, terabytes, those types of things. So once you get into like having a lot of something, you might use these as the prefixes. And then over here, if you're looking for something that is really tiny, you could use like micro, nano, and pico. All right, so let's try and pick out a couple that you might recognize. So centi, you can express this as multiplying your base by 10 to the negative 2, which is meaning the same thing as 1/100th. So it makes it small. So you can see all these are negative exponents. Those make things smaller. All right, a milli is a thousandth, so it's going to be a -3. Whereas a kilometer is going to be 1,000 base units make it. So this is bigger. This is 1/1000th of your base unit, where this is 1,000 of the base units, and then you would use kilo for that. All right, and then after the kilograms, you're going to notice, so these count as 1, 2, 3 when they're close to the base units, and then it's going to jump to get you to the next major type sizes here. So it'll go to millions, billions, trillions, but we're going to skip over like 100,000s and stuff like that. All right, number 5. Kind of silly thing here is I started answering them a little bit different than what they wanted, and then I realized at the last one I should probably like state the answer a bit different. All right, so milli means 1/1000th of something, and what they wanted you to put in the blank here is that that would represent a power of 10 that would be 10 to the -3. Of course, I didn't read my instructions here, and I was trying to think, okay, so what does a thousandth of something mean? As its decimal form, it's going to be 0.001. Okay, now I still think it's beneficial that you see this, so I left it in there, but I wrote it as 0.001 because that's 1/1000th. That's how you read that number, but it is the same thing as 10 to the -3 power. Kilo means 1,000, so I wrote the number 1,000, and that can be expressed as 10 to the 3rd power. Deci means 1/10, so I wrote that as 0.1, which is going to be 10 to the -1 power. But then when I got to nano, it's like 1/100000th. You know how many zeros I'd have to have in front of that? Basically, it's the number of place values I have. So like 1/1000th means I need 3 decimal places there. Okay, 1/10th means I need one decimal place that's in there. When you get to the billionth, I'm going to have 9 decimal places on there. So I was like, that's not going to fit. And then I read the instructions and realized, oh, they just want you to express this as a power of 10. As a side note here, which is kind of useful, base units, like just a meter, a liter, a gram, is 10 to the 0 power, which is equivalent to 1. So multiplying things by a 1 doesn't change their actual value type things. All right, and that might be might make a little bit of sense when you go back to the table and realize that deca is 10 to the 1st power, where deci, so that's 1 greater, then deci 1 less is going to be a -1. So your base unit is actually sitting right in between those two things with a power of 0. All right, so a lot of this activity is about giving you information that we're going to be able to apply to things later on. I know that I mentioned scientific notation, so that'll be one of them. 6, 7, and 8 is another thing that it's a typical question that you get asked a lot about things when we try and compare numbers, and we're not going to do a lot of it here with actual examples, but you're going to see it carry on into some of the other things we talk about in the course. All right, so how do we compare numbers to each other when we say something is blank times as bigger as another thing? Okay, with our metric system, it's very easy to say that like a kilogram is 1,000 times as big as I think I said kilogram. A kilogram is 1,000 times bigger than a gram, or a gram is 100 times bigger than a centigram. If you're just using the base unit, which would fall in between these things here, that's an easy way to talk about because it matches up to all of our tens and powers. But what if we have to compare something like a megagram to a hectogram? How do we do that if we're not using the base unit in there? Okay, well, a real simple approach to doing this is to take the larger unit that you have and just divide it by the smaller unit. Which, if you think about that, almost anything that you do when you compare sizing of things, you always divide the larger one by the smaller one, and that becomes your scale factor that's there. So we're still applying that rule here. But the neat thing about the stuff that's happening in this case is everything's a base 10, so you end up just doing a lot of quotient rule problems here. All right, so if we're going to compare a hectogram to a megagram, the larger of these is going to be the megagram, okay? Megagram is 10 to the 6th power, where hectogram is 10 to the 2nd power. So bigger exponents also indicate when something is larger. Okay, and then when we divide these two, you can apply the quotient rule of subtracting the exponents and you get 10 to the 4th power. So that means that there are 10 to the 4th power hectograms in a megagram. In other words, 10,000. A megagram is 10,000 times the size of a hectogram. All right, 7 millisecond to microsecond. Millisecond is going to be larger than the microsecond. It does give you a hint here to look at the negative exponents, because if you have small negative exponents, you're actually closer to the base unit, which means you're larger than the other one. So the milligram, like on the table here, let's see, this direction gets big, and this direction gets big. That's how it looks on there, okay? Let's see where we're at. Which one's going to be larger? That's going to be the millisecond. All right, so millisecond is going to be 10 to the negative 3 power, where a microsecond is 10 to the negative 6. Using the quotient rule, this one's a little tricky. I'll show it off to the side here. We're going to take negative 3, and so that's the top exponent, negative 3, and we're going to subtract the bottom exponent, which is going to change that into addition. So we get negative 3 plus 6, which actually turns out to be a positive 3. By the way, in all of these cases, if you're dividing a larger number by a smaller number, you will come back with a positive exponent. If you're getting a negative exponent, then mathematically you're either doing it wrong or you've got it upside down, sort of thing. So you can take that as a rule, that's true. 10 to the 3rd power, like if you don't like how this reads here, is 10 to the 3rd power times as large. You could substitute that with the word 1,000, okay? Millisecond is 1,000 times as large as a microsecond. All right, what else we got here? Kilometer is 10 to the 6 times larger than a millisecond. Oh, okay, so they don't give you the parts to look at first. You just want to pull them out of here. We have a kilometer, okay, and we have a millimeter. Okay, kilometer is 10 to the 3rd power, where a millimeter is 10 to the negative 3, so 3 minus negative 3 is actually going to be 3 plus 3, which gives you 6. And last here, hectoliter is going to be 10 to the 2nd power. A liter, that actually comes back to what I was talking about. Your base units are 0, so if it didn't make sense at the time, now maybe this will help out. That is going to be 10 to the 0 power. Your base units are just 0 power, so 2 minus 0 is still 2, so it's 10 to the 2nd power, or 100 times as large, which will probably make sense when you read, right? Hectoliter is 100 times as large as a liter. All right, part 2 of 2B. This one's going to be a little bit weird, I think. You're going to get introduced to some units. You've got joules, you've got watts, you've got kilowatts. You got some different things that are in here. You're going to get introduced to some units that you might not be as familiar with. And the truth is like, I'm not super familiar with them. I know what they are, but I don't like use them in everyday life. So I'm not going to make the assumption that you're very experienced with these things. The activity doesn't either, because they're really trying to set things up for the first few problems. If the beginning part seems a bit confusing and you're worried about whether or not you're going to be doing the problems, be looking towards problem 6 and then so on, and thinking that these are the types of problems you're going to have to do, and they're not going to get like way out there from what you see with the problems that are in the activity. All right, some things at the beginning to address. We have energy versus power. The words sort of sound the same, right? I mean, if you're really thinking about how much energy do you have, how much power do you have? The difference is that power is actually a rate, and a rate is one of those per something, right? It's usually per time kind of thing that goes along with it. All right, so energy, they describe it here as what makes matter move or heat up. What causes something to like push across the table? What causes something, well, you can read it, what causes it to heat up? All right, that unit that we're going to talk about is called a joule. All right, now power, which sounds a lot like energy, is actually the rate at which the energy is used. How fast do we go through our energy units? So you're going to see that as per a time unit here. Okay, the ones that we're going to be using is a watt. Okay, so energy is joule. A watt is going to be the same thing as a joule per second, because power is the rate at which you use your energy. So, but instead of calling it joule per second, we just have another name for it, which is called a watt, which may or may not be somewhat confusing on there. Okay, but a watt is the same thing as a joule per second. It's like an abbreviated name for it. All right, let's see here. 1 watt is equal to 1 joule per second. So that's what I was just talking about. Okay, if a light bulb uses 100 joules per second, how many watts is it going to use? And that answer is 100, because joules per second is the exact same thing as watts. Almost a bit sneaky there at the beginning, because it's just trying to get us to understand the definition, that these things are the same. All right, 500 watts is a rate, joules per second. So 500 watts is 500 joules per second, right? Because they are the same thing. Okay, what's nice about this though is it's showing you this as a fraction. Remember the per is that division. We saw this in 2A in that activity. And this might now start hinting towards using some dimensional analysis to do some problems in a little while. All right, next we have 1,000 watts is called a kilowatt, or 1,000 watts, right? Okay, so now we're bringing in what we were just talking about in the first part of 2B. All right, now we've got our prefixes to use in there. The reason that we'd be using kilowatts here is because watts, like a watt itself is a small amount compared to how we use energy, so you might want to talk about it in a larger form. It's sort of like if you're going to talk about the distance that you're traveling from one city to the next, you're not going to talk about it in meters, but you're probably going to talk about it in kilometers using a larger unit there. All right, let's see here. A kilowatt is kilowatt a unit of power, or is it energy? The fact that it's got the word watt on there is going to tell you that this is our rate type thing. This is the power that you've got there. Oh, and it has a little hint for you here. Is kilowatt a rate? Yes, it is. It is one. Until you get used to it, you really just got to go back up to the top and just sort of read what stuff you've got there. All right, let's see. Number 4, multiplying a kilowatt times an hour will give us a new unit called kilowatt hour. Called a kilowatt hour. Okay, but this, so if you see kilowatt hour, it really does mean we're going to multiply the number of kilowatts you have by the number of hours. Okay, and kilowatt is how much energy you're using per unit of time. Okay, if you use 0.1 kilowatts of power for 480 hours, how many kilowatt hours is this? You literally just take the number of kilowatts you have, which is 0.1, multiply it by the number of hours you have, which is 480, and of course when you multiply by 0.1, that's just going to shift the decimal from the back forward one spot, which is going to give you 48 kilowatt hours. So, is kilowatt hour a unit of power or energy? This one's a bit tricky here. Okay, hint, it's not a rate. They gave it this. So if it's not a rate, then it's not going to be power, it's going to be energy. All right, but the reason that that's going to work out is, remember that a kilowatt in the top has the joules, and on the bottom it's got the seconds, right? At a magnitude of 1,000 because of the kilo, but it's got joules and seconds. So then if you were to multiply that by hours, you think of that as like hours over 1. Even though these are different like units here, that's seconds and hours, they're both time together. They're a sense of time, and you can convert hours into seconds easily. And those units of time are going to cancel out with each other, which leaves you just with joules, and joules is just energy. They kind of give it to you. It's not a rate. It isn't a rate in there. All right, so number 5. Let's look at the actual comparison between 1 kilowatt hour and the number of joules we got. The blank's already telling you that it's going to be in the millions here. Okay, so a kilowatt hour. Okay, it's 1,000 joules within 1 second. So kind of going back to what I was looking at here, but at a factor of 1,000. So instead of 1 joule per 1 second, it's 1,000 joules per second. If we were to multiply, that little dash right there does not mean like a minus sign, it's just a hyphen. But you need to understand that means multiply. We'd multiply it by 1 hour. But since hours don't match seconds and we can't really cancel directly, we're going to convert the hours into seconds by using our conversion unit conversions that we've got. So 1 hour is equal to 60 minutes. It's going to take out the hours part. 60 minutes, okay, we want to change that to seconds. So 1 minute is equal to 60 seconds. The minutes will cancel, and now we've got seconds, which can in fact cancel with those seconds. And when we multiply, let's see, we got all the bottom is 1, so you don't need to worry about that. Across the top here, you're going to have a 60, a 60, and 1,000. All right, so 60 times 60. I'll do it in the calculator so you can see it, but talk about a little bit of the math. If we do 60 times 60, you're going to get 6 times 6, which is 36, with 2 zeros on the end. There you are. But then when you multiply that by 1,000, you're really just going to add 3 more zeros onto the end of it. So it looks like this. So you get a total of 5 zeros and a 36 in front. So 36, 1, 2, 3, 4, 5. Then working from the back, I'll just add some commas in here. Okay, because that moves up to thousands. And then one more comma right there. We can see this is going to be 3,600,000. 3,600,000. So instead of writing that full number in here, we're going to use the word million so that we can drop off all these extra, they call them periods here at the end. And this will be 3.6 million joules. Next, what we're going to do is start putting together the information that we've talked about to calculate some things. Primarily here, what we're going to do is calculate how much your electricity is going to cost you, sort of thing. All right, so number 6, you actually have a little picture here of an Austin Energy bill, and they have blocked off a little spot here that says kilowatt hours used. Okay, there's some other things we're not going to look at there, but this is kilowatt hours used within, I think this is the month range. Yeah, service is 31 days. All right, so question A, how many kilowatt hours of energy were used that month? 1,157, just taking that number there. If Austin Energy charges 11 cents per kilowatt hour, how much is the bill going to be? Well, you need to multiply those numbers. That's really all you got to do is multiply the number of kilowatt hours by the price that you're going to pay for each kilowatt hour, which is going to be 11 cents, and that'll give you 127.27 cents. But looking at it in that dimensional analysis form is kind of cool, that just so you can see that your final units are supposed to be money. We start with our 1,157 kilowatt hours over 1. We then multiply it by a unit conversion, which is that 11 cents is the same thing as 1 kilometer or 1 kilowatt hour. Those are the same thing. So it's sort of like your 12 inches in 1 foot that we saw before, but we're saying that the price of a kilowatt hour is 11 cents. So if you set that up as a fraction, multiply it, these units will end up canceling and you get just the money units that go with it. Now, you can do the whole math by just multiplying and get it, but this is a really neat throwback to what we did in 2A and see how like dimensional analysis works within these problems. Or the fact that we use dimensional analysis all the time and we didn't really know that it could be written out like that. All right, C, how many joules of energy are used? We're going to answer in the millions because it's a big old number. All right, these are the kilowatt hours. All right, now a kilowatt hour, we already calculated up in this box here to be the same thing as 3.6 million joules. So we want to be able to, just convert like into generally what the joules are, and we'll use this factor or this conversion factor or units, and again, set these up so that they're on opposite sides of the fraction. They'll cancel out, which will leave you with your units as million joules. It's kind of neat that those are your units. And all we have to do is multiply 1,157 by 3.6. Don't actually add all the zeros on because we just keep all that millions in that. And you end up with 4,165.2. Here's on my calculator. That's what you end up with, as in millions. Which means you're really in the billions, right? Because 3 more spots would be in the billions, but we'll just state the answer. So question number 7, what we're going to do is calculate the kilowatt hours and then multiply it by a value that's going to show up in number 8, a value as in like a price to see how much something's going to cost us. All right, so here's what we've got. We have a 100-watt light bulb. Okay, so now we're really thinking something that we know that we're used to. Usually in your house you have 60-watt light bulbs, or 45. All right, but let's say we have a 100-watt light bulb, and somewhere it's going to say that you leave it on. Assume the bulb is turned on the entire month. So yeah, the switch was turned on, and we're not worrying about on and off, all that business. Okay, so first question, how much energy in kilowatt hours does a 100-watt bulb use in 1 month? All right, A, since we are finding kilowatt hours, which 2 quantities will you need to find? And then multiply. That would be your kilowatts and your hours. We need to find out how many kilowatts, and then we're gonna multiply by the number of hours that have passed, and that'll give you your kilowatt hours. All right, so let's see here. The light bulb that we have is a 100-watt bulb, right? It doesn't even actually get to 1 kilowatt, because a kilowatt would be 1,000. It's actually just a tenth of that. Okay, so we're going to convert that first. And it looks a little bit more complex than what you're really doing. What we're going to be doing is just taking whatever our wattage is of the bulb and then dividing it by 1,000. If you divide it by 1,000, then it puts it in terms of kilowatts. Okay, so I'm taking 100 watts, dividing it by 1,000, and it comes back as 0.1. Okay, 1/10 of a kilowatt is 100 watts. Okay, so no matter what type of watt we give you for a problem, just divide it by 1,000 to get it in terms of kilowatts. All right, now that we have that, what we're going to do is take our time frame and make sure we have that in hours. So they told us that it's going to be on for an entire month. They also want us to assume it's 30 days here. Okay, so 1 month. 1 month is the same thing as 30 days. So that'll cancel out your months. 1 day is the same thing as 24 hours, so we can cancel out our days. And if we multiply 30 by 24, because everything else is just ones, 30 times 24 is going to give you 720 hours. Okay, so here's what we found. We found that kilowatts is 0.1. We found that hours is going to be 720, which means that our kilowatt hours is going to be the product of those 2 things, which we're going to look at right here. Here's your first part, 0.1 kilowatts, multiplied by 720 hours. We saw this earlier that if you multiply by 0.1, you're gonna actually move the decimal back a spot, which is gonna give you 72. So we get 72 kilowatt hours. Let's just write that over here. 72 kilowatt hours. With everything else that we've written there, and I think with the blanks in the words, sometimes hard to see the answers. That's it right there for you. All right, so 8 is a follow-up to that. Now it says, hey, let's see, if the utility company charges 12 cents per kilowatt hour, how much are you gonna get charged? Well, just multiply that by 12 cents. So again, that's 0.12 because it's cents. So I already got the answer there, but I just showed it to you. Take 72, multiply by 0.12, and you're gonna get $8.64. All right. All right, then number 9. The reason that I have number 9 blank is because I don't really like doing it in this long drawn out way, where the shortcut for it pretty much makes it a lot faster. Okay, so it says, suppose that you replace a 100-watt bulb with an energy efficient 20-watt bulb. So you're gonna be using less wattage, right? How much money will it cost and how much will you end up saving? Okay, well, here's the deal. Like if you look back at everything that we did, we took kilowatts, we multiplied it by hours, we then multiplied it by money. Everything's just multiplication across the board. So if you're just going to change one of these pieces by a certain factor, then it changes the final answer by that factor, right? So I could just look at the wattage part of this and say that if it started at 100, but now it's changing to 20, All right, how do I go from 100 to 20? You actually just divide by 5 to get there. Remember, division, multiplication, inverse operations. Okay, so this will work fine. They actually refer to it as 1/5 here, so you see it as a factor, but it's the same thing as divide by 5. So if I were to cut down one piece, say the wattage by a factor of 5, just divide it down by 5, you can actually just take your final answer that you previously had and divide that by 5. So take 864 divided by 5 and you get $1.73. Now the same thing can apply to any part within here. If the number of hours that you use it is cut down to 6 hours a day, and instead of doing 24 hours, you're doing 6 hours a day, to go from 24 to 6, you just divide by 4, then you could also just divide the answer by 4. Because everything's being multiplied, any kind of factor that you see, just interpret it as division and apply it to the final answer. And then that way, you don't got to do all of these things to get something that's as simple as just dividing by 5 with that. All right, then this question, how much will you save? So you're paying that much. That means you're saving the difference, which is $6.91. All right, last question here, number 10. Suppose you have a clothes dryer that uses 4,000 watts of power and you run it for 2 hours each day. If the energy company charges 12 cents per kilowatt hour, how much will you spend to run your dryer each day? Okay, so for the day, we're gonna be running it for 2 hours. Here's our parts. Let's see if we can show these. You need to know your kilowatts, you need to know your number of hours, and you need to know your price. Look, number of hours we got, it was 2. They just said it was 2. The price we got, it's 12 cents. Okay, so the only little kind of work we got to do at the beginning is to get your kilowatts. They tell us that it's 4,000 watts. Remember, take whatever your wattage though is and divide that down by 1,000 to get it in terms of kilowatts. So if I divide 4,000 watts by 1,000, I get 4 kilowatts. Okay, all right, so then it's just becoming, if I follow what I have up here, it's going to be 4 kilowatts multiplied by 2 hours multiplied by 12 cents. I broke it up into a couple steps here when I originally did it, but ultimately that's all it is. It's those 3 things that are getting multiplied together. So you can get 8. 8 times 0.2 is going to be 96 cents for that. All right, part B. How much money will you save each day if you replace the dryer with one that uses half of the power? We're changing a factor, one of the pieces by a factor. One of the components is we're changing by a factor. So if it uses half of the power, that means if it's using half of the wattage, how's that going to change your bill? It's going to cut it in half. As I described before, however that changes one thing, it changes the whole thing by the same amount. So that ends up cutting it down by half, down to 48 cents. And a follow-up question, how much money will you save in a year? We're going to assume that that a year is 365 days. So you would have been paying 96 cents a day. You're going to be saving half. So you're going to be only being charged 48 cents a day for that. The other problem's a little bit different because it's what you pay and then what you save are different numbers after the change. And then here's the same thing, what you save and what you pay, because it's a split in half, it's 48 cents. So we can just take the 48 cents that you were saving every day, multiply that by 365 days, and you're gonna get 175 and 20 cents, which is that one.